Hello everyone. Here we are presenting our project Stabilization of High-DoF Dynamical System using Low-DoF LQR trees. This is the outline of our project. We'll begin with motivation, then we'll see some of the related work that is prior to our project. Then we'll see the dynamical systems that we use to investigate our problem. In that we'll see the compass gate and the neat compass gate model. We'll see how their dynamics are derived. Following that, we'll see the core of our project, which is the methodology involved. In that, we'll see the LQR trees and the LQR tree for the limit cycle, which is our work. Then we'll see the results, conclusion, and future work. Here is the motivation for our project. The world is built for humans, and walking robots are very similar to humans in the way they navigate. Walking robots have a great accessibility, and this is one of the key reasons why the robotics research community is very much interested in the walking robots. In general, walking robots have two types of gate, the dynamic gate and the static gate. The static gate is very inefficient compared to the dynamic gate. In this picture, you can see the Atlas robot exhibiting a static gate in comparison to the human, where he easily exhibits a dynamic gate. So the graph here shows the nominal trajectory of the walking limit cycle. In order to follow this walking limit cycle, you need to have built a controller. From the property of the controller, there are some states that lie close to this walking limit cycle, which can be stabilized back to this nominal trajectory. Those regions are represented by gray here. But there can be states outside this region also. So to stabilize those states, we need to do some motion planning techniques to bring back those states back to this funnel. This is some of the previous work for our project. The model compass gate in which we investigate our algorithm was first built by Megier's group. He actually designs a compass gate model with planar links and mass concentrated at the center of the links. There was another variant of the compass gate, which is the compass gate with the knee. Some of the domain specific work are a paper called A Robust Limit Cycle for Leg Locomotion. In this paper, the author comes up with an limit cycle that is robust to states that are close to the limit cycle. He comes up with an optimization problem to solve a limit cycle like that. But that limit cycle is not, the states far away from the limit cycle cannot be stabilized to that limit cycle. So in order to completely fill the entire state space with policies, there is an algorithm called LQR trees. But in the original version, this algorithm works only for a goal point, not the goal trajectory or goal limit cycle. We extend this original paper to a goal limit cycle.
The systems we will be investigating in this project are a compass gate and a kneed compass gate. These are two simplified planar bipedal walkers that are shown here. The compass gate is shown in the top right. There are two angles that define the system. It has also masses in the middle of each leg and one at the hip. The kneed walker, which is shown below, is defined with four angles since it has two knees that can also bend. In each system, we treat one of the angles as a pin joint about the stance foot and the ground. The general dynamics for the compass gate and for the kneed compass gate are well understood and are shown here. An interesting feature of the compass gate and the kneed compass gate are some discrete acts that happen during the course of walking. For example, when the compass gate switches the stance leg to the new stance leg, there is a loss of momentum that goes into the ground. In order to model this physical phenomenon, what we do is we calculate two matrices which symbolize the angular momentum before the collision and the angular momentum after the collision, and we equate them. It's critical that when we're doing these calculations, we choose a joint which is unactuated. For example, the momentum is conserved about the previous stance foot and about the new stance foot, but is not conserved about the hip, which is actuated. It's critical because the change in momentum, or the conservation of momentum, is directly caused by the net zero external torque. The matrices that we use for the compass gate inelastic collision with the ground are shown here. When we move to the kneed walker, we have a similar situation when we switch from the old stance foot to the new stance foot, but we also see another collision. This collision is the collision between the lower leg and the knee. With more detail, we can see here the exact derivation of how we calculate the conservation of momentum about the stance foot and about the knee during collisions. It's clear that the tangential velocity of every point can be defined based on the rotation of the individual joint about the individual limb about its connecting joint. What we have to do is we have to use the formulas shown here, showing uh, the mass of each point with the angular velocity crossed with the tangential velocity, or multiplied with the orthogonal velocity, in order to create the angular momentum that we see here. As I mentioned before, angular momentum would not be conserved about a point such as the knee, since it's actuated, and thus the net torque is not zero. Here we can break down, again, in greater detail, how the conservation of momentum occurs during the collision at the knee. On the left, we see that the shin is moving with some velocity, and then we see on the right that it is locked in the knee-locked position, and now its velocity becomes tangential to its new rotation about the hip. The formulas that govern this phenomenon are shown here on the right.
So in order to work with the need compass gate, we built a custom software. The Drake comes only with the compass gate plant and visualizer. Uh, we separately built the need compass gate in the knee locked mode and in the knee unlocked mode, and a visualizer for it also. We generalize the model so that it can be inherited from the parent class, and it can be used in general to do all the further LQR tree strategies required. Before we jump into LQR tree algorithm, we'll look at what a funnel around a trajectory means. So the LQR tree algorithm uses a series of trajectories that eventually end into the goal trajectory. So here is one such trajectory that has the start point at red and ends at blue point. Our idea is to come up with a controller that stabilizes the system around this trajectory, but we are allowed to be uncertain. This is because the trajectory that is following this trajectory uses a controller that can accept any initial state that is inside this blue ellipsoid, and it can stabilize those initial states. So this controller is allowed to be that much uncertain. So under the TVLQ policy, the set of all points around the trajectory which end up inside this blue ellipsoid is called the funnel around the trajectory. For a TVLQR, the funnel is captured by this equation. And the main thing to note here is that the funnel around the trajectory is the property of a controller. So for a better control design, we are going to have a bigger funnel. So here is the LQR tree algorithm itself. So first we add the funnel of attraction of the goal trajectory itself into the tree. Now we sample a new point and we find the nearest point in the existing tree according to the cost to go metric of the LQR controller. So we find the point that is nearest to this according to that cost to go function given by this, and we plan a trajectory from the sampled point to this nearest point using trajectory optimizers. So we'll be using a direct collocation method to plan this trajectory in blue. Now we apply TVLQR controller to stabilize this trajectory. So we don't just execute these trajectories in open loop in the real system. We use TVLQR controller to stabilize the system around this trajectory, because of which we get these funnels. So we add this new funnel to the existing tree. Now we sample a new point and we repeat. So we sample a new point, we find the nearest point according to the LQR cost function metric in the existing tree, and we connect it, and we verify it. So we continue doing this until we considerably cover the state space. So what we have here is, before we had this LQR tree algorithm, we just had the funnel of attraction around the goal trajectory. So the controller can only stabilize those states that is around this green trajectory. Now what we have is that we have a policy for any state outside this region of attraction, because we pre-computed it. So how does it work in real time? That is, once we have this LQR tree algorithm in the real robot, when the robot is perturbed so much that it leaves the region of attraction of the goal trajectory, we are going to find ourselves in one of the funnels. For example, let us say this green X mark is our initial condition after the perturbation. So we find the nominal
control input for this funnel that we fall inside. We apply those control inputs. We because of our control design, we make sure that we are inside the funnel as long as we apply the nominal control input of that time varying LQR controller, and we end up inside the limit cycle. So once I'm inside the limit cycle, I have a TV LQR controller for the limit cycle itself, which is going to stabilize me inside here. The one thing to be noted here is that there are some parts in state space which are not covered yet by funnels. That is because there are some states for the compass gate, and compass gate is an underactuated system, and there are some states for compass gate which cannot be stabilized. For example, a lying down compass gate cannot get up and start walking just with an input at its at the middle. So here is the whole algorithm in one slide. So initially we sample, we add the funnel of attraction of the goal trajectory to the tree. We sample a point at random. We plan a trajectory from the random sample to the existing tree. We then stabilize this trajectory that connects these two. We add it to the existing tree, and here we have the termination criteria. That is, if the number of if we have 500 consecutive samples that fall inside the funnel of attraction each time we sample in this algorithm, we are going to say that the whole state space is covered and we are going to terminate.
Here are the experiments that we conducted. In this model, we see the compass gate that is walking without the LQR trees and with the LQR trees. So in the first case, there is only velocity perturbation that is given to the compass gate. In the second case, there are both velocity and position perturbation that is given. So without the compass gate, without the LQR trees, the compass gate is unable to stabilize, but with the LQR trees, you can see that the compass gate stabilizes and come back to the limit cycle. So these are the phase portraits of the two cases mentioned above. In the first case, you can see that there is only perturbation only in the velocity, and in the second case, the starting position is far away from the limit cycle and it has both velocity and position perturbations. So we do direct collocations to come back to the limit cycle. So this is the table showing the results that we got. To completely fill the state space with the LQR trees, it took us 6 hours. The number of samples of the LQR trees are 252, and you can see that the number of nodes are 192. We compare our LQR trees that we had built for the compass gate with the two previous works that shows the LQR trees built for the pendulum and the card pole. The red one shows one of the variant of the LQR tree, and the blue font shows the other variant of the LQR tree. We took the verification by optimization of the LQR tree shown by blue. Every iteration of the LQR tree has numerous direct collocations, which is one of the trajectory optimization method, and in that we see that the average time for the direct collocation is 14.7 seconds, and that is why it has taken a lot of time to finish completely filling the state space with the LQR tree. So we conclude our project with the advantages and disadvantages. The main advantage is that this is one-stop shop for filling all the entire state space with the um, policy, such that you can recover from any point in the state space back to the limit cycle. Uh, the main disadvantages is it's the time taken to completely fill the state space, but once the planning is done, there is no requirement for planning again during the execution. Another disadvantage is that since LQR is an linear, it's based on a linearization. There are some systems which cannot be controlled when it is linearized. For such systems, this method cannot be applied.
One very interesting application of LQR funneling would be in order to apply a LQR funnel that has been derived for a lower degree of freedom system and apply it to a higher degree of freedom system. This is where the need walker comes into play. We're proposing that it may be possible to use the LQR funneling that we've previously discussed for the compass gate walker in order to actually control the need compass gate walker in situations where it might lose stability. In order to do this, we need to create some sort of mapping that will tell us, first of all, how we can translate the higher degree of freedom state into a lower degree of freedom analogous state in order to actually look up from the LQR funneling what the control effort might be. And then once we found that control effort, we need to then create another mapping function that will make a 4 degree of freedom control from the lower degree of freedom LQR solution. We've proposed a couple methods. One would be in order to use principal component analysis. This might tell us, using principal component analysis, how the higher degree of freedom system can be effectively reduced to a 2-degree of freedom system by eliminating either unnecessary states or possibly recombining states similar to a singular value decomposition, and then reducing the 4-DoF system into a hybrid 2-DoF system. The number 2, which is pictured at the top of the screen, would be to immediately have the higher degree of freedom system assume the same shape as the lower degree of freedom system, and then from there apply whatever efforts are mandated by the LQR system. The third option would be a dependent actuation. This would be mimicking a rigid link connecting the upper limbs with the lower limbs. Basically what would happen is we create some sort of profile that would map every input to the top 2 degrees of freedom, which is similar to the compass gate, to our extra 2 degrees of freedom. The number 4 and final recommendation that we propose is to basically approximate the High-DoF system as the compass gate system. And so there's a couple ways of doing this. We might be able to just use the foot stance positions combined with the hip location to create a pseudo compass gate, or we may be able to use the center of gravity of the higher degree of freedom system and then equate that to a lower degree of freedom system with a similar center of gravity. One interesting consequence of this may be that it might be necessary to calculate the LQR funnels for multiple types of compass gates in order to be able to have an applicable control input for a compass gate that is not exactly the same parameters as the one we might have started out with. So moving on to future work, we do need to solve the need compass gate system errors. Currently our need compass gate system, which we created custom in Drake, has some issues, including what can be seen here on the right. There's some collision logic that's not making sense, given that you can see the knee goes past the mandated collision state into a positive angle value. And at that point, we're not following the exact laws that we should be mandating for our need compass walker. We also would like to integrate the LQR control inputs into the High-DoF Drake plant. So now that we have our funneling system, and we've done that for our compass gate, we need to basically channel that and input all of those control lookups into the need compass gate system once it's working. Then once we have that system set up, we'd be able to test those model reduction methods that I've discussed previously. We would then determine the test for robustness and pit them against each other to see which one functions the best. Thank you so much for listening. We look forward to hearing your input.